see quite an audience. The goal of this talk is not about fundamental new things in R, but actually, as you will see, I was planning to teach a little bit about numerical issues that I would like more R users and R programmers particularly to be aware about when they do numerical stuff, even statistics. That's the outline. There will be basically two parts, namely what is current in R and some bit more people should know about, and then the last thing is about my package Rmpfr, which is also, it's an interface from R to a library for arbitrary precise computation that has also existed for a little while. Okay, preamble is really and I think the person is not here at the moment. This is from an old, 4 years ago, talk on good practice in R programming. I talked about guidelines for good programming, and rule number 4 was to learn from the masters. And an R, because I was emphasizing R programming not just as a science but as an art. You learn art from artists and from the masters, from Picasso to Klimt and Monet. And in R and S from John Chambers, Bill Venables, Bill Dunlap, Luke Tierney, and so on and so on. And one of the S masters is an Aussie, and you've mostly all heard him, and I wanted to give kudos to Bill Venables. And remind you, read other people's source code. That's how I learned a lot of programming, by picking code other people I knew were good or I guessed were good and learning from them. Okay, now to the real talk. As many of you know, R is accurate to 16 digits, which is not quite true, but that's at least good to remember. Why is that? If you look at the machine data, which in principle describe the properties of your current platform on which R runs, but the parts I show here are actually universal now on all platforms, as far as I know that R runs typically. But maybe it would be different if R ran on an ARM processor, but I've never seen it. So what the number typically has, it has 53 digits for the mantissa. Okay, now I should. Yeah, sorry. So 53 digits, what's called double digits, and or here, and then there's the exponent with another 11 digits, and that's what the 64 digits make. The exponent has a sign, of course, so it's only 10 bits for the exponent. That's why the exponent, the binary exponent, is maximally 1024. Good, that's just kind of keep in mind. And of course, because of that, if you take a difference between this number and 1, then you don't get 1, 2, 3, 4 something, but you actually get 2 to the power of 16, because here it's really the 16th digit around here. So that in some sense you get, instead of a correct, formally, mathematically correct answer, that would be 1.2. 10 times 2 minus 16, it's about 2 times more. Of course, that's all expected, but sometimes people are not aware of that and ask questions because of that. And this is not a perfectly good example, but an easy one to show in a presentation of cancellation. Actually, it's a little bit different. And cancellation is really the most important accuracy loss that happens, and that sometimes unavoidable and often is avoidable with smart thinking, but a lot of it happens in your packages and in other people's packages because people didn't consider it. Okay, so the third section, the only FAQ that is really very frequently asked still, I think, is 731. Floating point numbers are limited is my section title to that. And the fact is, why doesn't R think these numbers are equal? Maybe that's actually the example from the FAQ. You take the square root of 2 in R and you square it and compare it to 2, and then R tells you, well, no, that's not the same thing. Even though mathematically, you know, it should be the same thing. And, if you're slightly smarter than the people just asking the question, why is R wrong here, you can compute the difference and at least get an idea of why it's not the same. And here you encounter what I forgot to actually say. Along is the first thing here, the double epsilon, the computer epsilon is, these two numbers are two versions of the computer epsilon. That's the number which, when added to 1, actually is 1, and it's the largest number with this property. And these two are two different versions with slightly nuances about it. 53 versus 52-bit precision, and both appear in some computations. So anyway, so we actually get here 2 times the computer epsilon, which matches the fact that we're comparing to 2 and not 1. So actually, R is using the best computation that it could, and of course it's not R, it's really the underlying C math library that does this. There's this reference that is also part of the FAQ. It's actually a relatively long reading. It's almost 40 pages, more than 40 pages, but much of it is worth reading. I look and take a slightly different version of it just to make those aware of you who don't know about it, and maybe people who read the slides afterwards. So this is closer. Koenig and Plohr, one of them the originator of C and I think even Unix, wrote in one of their programming books, 10.0 times 0.1 is hardly ever 1, which was true at the time, and interestingly with IEEE or modern double flow precision, it's actually often true. This one is true in R, and versions of it replacing 0.1 by 0.2 and 5 by 10, so it actually matches. But there's a version of that where people get really confused and ask these FAQs. So I take I take a sequence of 1/10, 1/10, 2/10, and so on, and subtract 1/10 less, right? So that gives 0.1, 0.1 all over. But when I compare this with 1/10, it sometimes gives true and sometimes gives false. Actually, more often false than true. And so people say, well, R cannot even do this. I can do this. I can do this since grade 5, or I don't know when you learn. And even more so, if you ask about the unique values of these 0.1, it's actually got 4 different versions of it. And that's no mistake. That's the reality. And of course, we should do graphics, and so I just take, actually, instead of just 11 of these numbers, I do 31 of these, subtract 1/10, and then now, of course, we are in the famous computer epsilon scale of 1 to the minus 16. So we actually see it even more. 1, 2, 3, 4, and 5 different versions of 1 divided by 10. Or it didn't even count, so it's 6 different versions. And of course, it's because you are subtracting, and all of these numbers are not exact. They are infinite fractions in a binary arithmetic. Only if your number if your denominator is a multiple of 2 or 5, or products of those, then you have an exact representation. Oh, not 2. Forget the 5. If the denominator is a multiple of 2, then you have an exact fraction in some binary version. Okay. More importantly, things that have been in R since R version 1 or quickly after, and that still not enough people use. More to statistics, computing likelihoods, and the likelihood being the product, in the case of independence, product of density values. They easily overflow or underflow. Often they are very small. Often n is relatively large, in big data situations even more, so you easily get 0 here, or infinity because of an overflow and etc. Or if you multiply probabilities, the same thing. And so the solution is to work in log space, and there's more about log space I won't talk about here, but to do likelihood, you compute the log likelihoods, and instead of this product, you get the sum of the log densities. And the similar thing for probabilities. But we don't have to stop here. So if you did this, then you would take log of my f times plus log of and so on. But R can do this for many distributions more accurately itself. And that's why we have the log argument to all the density functions and the log p for probability to all the distribution functions. And I see that people don't use this so often. I mean, all of you do, or most, and but I hope some of your students can read that, or if you haven't heard about it. And it makes a big difference, because if dnorm becomes 0, and that's very quickly, like 10 standard deviations outside, or maybe a little bit more, it underflows to 0, and then it doesn't help to take the log afterwards. You get minus inf, and then the whole sum is actually broken. So use the log arguments in dnorm and pnorm, and don't take log of these. I also see this in packages that people don't do that. Next thing, why R has needed even more functions. And this is now more common knowledge, because the C standard and the math labs have started to implement these. But at the time we introduced this in R100, which was 29th February 2000, this was not part of the C libraries yet. And so the function log1p computes just log1 plus x mathematically. And so why do we need another function if it just does something simple like that? And the inverse function of that is xn, x minus 1. The reason we want to do this is again some versions of cancellation. For the second one, you easily see that when x is small, then e to the x is basically 1, and so we have a lot of cancellation here. And it's not necessary. If you already know that your x is close to 0, you can be much more accurate than doing this. And the same here, log of 1 is 0, and if x is close to 1, this quickly loses, as I showed in my initial example, this quickly loses most of the precision in x. You add it to 1, and then actually you go back to 0. You can do much better than that. I show for the first example, I show just you can do that yourself. There's nothing fancy here. I use log1p, and I use log1 plus x, and compare it when x goes from 1 to the right here to 0 on a log scale. And what I show here is the relative error computed and the absolute value of that, so I can take a log scale also here, not only here. So the relative error is the absolute error divided to the true value, so this can be simplified to 1 minus the ratio of the approximation to the true value. Here I assume that the algorithm of log1p is correct, which I know it is, but of course in theory I would use my stuff or something else to get the really true values. And you see that for 0.1 you already use about 2 digits if you use that, but like 10 to the minus 16, if the error is 10 to the minus 16, that's the best we can have. If you have 10 to the minus 14, you have lost 2 digits, and so on. And so if you go closer and closer to 0, then you cannot use log1 plus x anymore. And what's the solution here? And often is actually using Taylor, using basic calculus, and of course in implementation people will do something smarter because they don't want an infinite series. And but anyway. Basically, I mean, for very small x, log1 plus x is just x. And then maybe you need 1 or 2 terms if you're around here, and you don't use any precision, and it works. The similar thing for xm1. I see log1 plus or log1 minus, like that's the same, very, very often in code. And that's only okay if you are sure that your x can never be very close to 0. Because otherwise you unnecessarily you lose much precision, up to complete. I mean, this is complete catastrophic precision loss when your relative error is 1, then you are a factor of 2 of the true value. So use log 1p instead of log 1 plus or log 1 minus, log 1p of a negative number instead of log 1 minus. Okay, there are more such things like cos pi and sin pi, tan pi, more recently in R that help you to compute cos of pi x and similar to be exact at 0. That's, in my view, less important, but still. The last thing is something that I want to raise a little bit and give you some more slides. If you divide the function name that I used, I've later seen it used in other libraries, C libraries, other language libraries. If I'm different, it's the same idea of log 1p and x minus 1, but here you have a mixture of both. Log of 1 minus x to the minus x. So you can think of, oh, that's log 1p of minus x. Or you can say, oh, okay, that's the log of negative of xm1, if you remember xm and log 1p defined as these functions. But interestingly, sorry? Thank you. Interestingly enough, it's not good to do that, and this is not something academic, this is something that is really needed in the logistic distribution, also sometimes in computations for logistic regression. The first curve looks fine, no problem here. If you go a little bit further out, here I only go to 10, if you go further out to 30, then you suddenly see it jumps from going in log scale again, it goes down, 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 and then it jumps directly to 0 or to minus infinity in this case. Here I now use Rmpfr, the package I mentioned, the Rmpfr, and here I can make, instead of a double precision number, I want to make a number that has 120 bits accuracy, and I can compute these numbers here, and instead of 0, 0, 0, coming from the right now, and then jumping to 10 to the minus 16, I get the true values. And I see that even in the log scale, it's minus inf minus inf minus inf, jumping to minus 36. They are actually also wrong. True values are something like almost 37, minus 37, and so on. Or visually, the blue values are using double precision, and the red values would continue to use the package Rmpfr with the function that creates these numbers. And by the way, so the solution to the log 1 mx that has been in R for a long time now, but only in the C code, is you use one version, the log of xm1, in one case for small x, and you use the other one in the other case. And you have to do some switch, because using one of them for both extremes would really lose precision in that case. And interestingly and beautifully enough, the optimal cutoff is log 2. Seen in the vignette to that package, so I have a few minutes left. This is package Rmpfr, multiple precision floating point. Reliable, that's the MPFR library, is the GNU C library with other interfaces than just to R. In R, I use S4 classes to nicely model these numbers, even matrices of these numbers. One last example that I only very, very quickly want to allude to. If you want to compute alternating binomial sums, and this sometimes happens, for instance, if you take discrete differences instead of derivatives, this is a very ill-posed problem, and you have no chance to do this when n goes to 50 or so in usual arithmetic. And it's kind of known, or you find it, and you have to use some higher arithmetic. And here there's the red thing is the thing that works, and the black thing is on top of the red, and here it explodes really to plus and minus infinity. And we can zoom in, the relative error, even at 20 terms you have already lost about 6 digits, and at 30 terms you have lost all digits basically. Okay, the summary, use double precision is not always sufficient. Use the log arguments to the dp and q functions. Use log 1p and exponent. There is this function, which actually is in one of our packages, but basically in R. And you can use the R package Rmpfr if you want to really check accuracy in your computations. Thank you.